So, we stopped here and I briefly pointed to this and said how we compute the energy that is intercepted from the sun by each square meter on the earth, and then I showed this figure and said we looked at the incoming 100%, how much is reflected back, total of about 30%, and I said the rest is long wave which has to balance the outgoing short wave. The details of doing this are basically to go back to a square meter, look at the short wave coming in and outgoing long wave which is black body radiation, the Stefan Boltzmann law, and then you have to do the calculations to show how much heating is added by the greenhouse effect. So, this calculation is very simple, but it will be provided separately as a module that you can follow up. To continue the discussion in this broader context of climate introduction, you look at the equator to pole heating imbalances. So, you basically take the whole globe and you make the average over all longitudes and you look at the distribution from the equator to the pole, and you see that the northern pole is here, southern pole is here. At the top of the atmosphere, the arriving shortwave radiation is distributed like this. There is more radiation at in the low latitudes and low radiation at the high latitudes, basically because the earth is tilted at 23.5 degrees to the orbital plane, which means the poles are pointing to the sun for 6 months, pointing away from the sun for 6 months. The tropics are kind of receiving sunlight at a similar rate all year long. So, when you make the yearly average over all longitudes, this is the distribution you get. Then you look for what is actually absorbed at the surface. How is that determined? As we said before, there are various things that are reflecting the shortwave radiation. So, here is a yellow colored line showing the reflected shortwave radiation by the clouds, and you can see that there are always clouds at almost all latitudes, but in the tropics because of the rain there are deeper clouds. So, they have slightly more reflection, but the reflectivity of the cloud depends on how high they are, what is the cloud top temperature and so on, because they are also reflecting like black bodies, and you will see in the module that the reflection of energy from black bodies is dependent to the 4th power of temperature. And reflected at the surface, again it is very high at the poles, that is the first thing. I think you can immediately imagine why that is, because there is snow and ice at higher latitudes. At lower latitudes, the reflection is mostly from land or the ocean, which is relatively lower. The other point you see here is that the reflection is not symmetric, even though the received energy is symmetric, because the continental distribution is asymmetric, because the southern hemisphere has the southern ocean and the Antarctic subcontinent, the distribution of albedos and energy received is not going to be symmetric. The temperatures are not symmetric either. So, if you put this all together, what is the net energy? You again look at the averaged over all longitudes and so called meridional section that goes from the equator to the poles. You can see that when you look at the short wave energy coming in and the outgoing long wave energy, there is a surplus of energy in lower latitudes. At higher latitudes, the outgoing long wave together with the reflected solar radiation makes it so that there is a constant energy deficit. So, they are actually losing energy to space. So, if you did not move the energy from where it is access to the regions where it is deficit, then you will constantly heat up the regions which are receiving more energy, you will constantly cool down the regions which are losing energy. Obviously, this does not happen because tropics are warm, poles are cold, but they remain at similar temperatures over hundreds of thousands to millions of years with small variations. They are not constantly cooling or warming, which means we are somehow moving the energy from the surplus region to the deficit regions. How are we doing this? Basically through all the winds, the circulation, the ocean currents and so on. So, the hurricanes, tornadoes, monsoons, everything is a part of transporting the energy from surplus regions in the lower latitudes to deficit regions in the higher latitudes. So, once you put together the detailed energy budget calculations to this kind of average distribution of energy, you want to see how that energy is related to the temperature difference from the equator to the poles, how that temperature gradient from the equator to the poles is changing with global warming, for example, or how it has changed in the past, that tells you how much energy is being moved, how much energy has to be moved. That tells you how climate changes, how the precipitation distribution changes, how the winds change, because they are all trying to balance this energy all the time. So, that is kind of a unifying theme you can think of. We will keep coming back to the details as we go along in terms of how the feedbacks affect this circulation and the energy transport. So, the albedo or the reflectivity of the surface has a range going from very high 60 to 90% reflection for fresh snow or ice. You can imagine that snow looks very bright from if you look from the aircraft or from a satellite. Old melting snow has little lower, desert sand has 30 to 50%, clouds depending on whether it is a dark cloud or a cloud top temperature is very cold, it can be very highly reflective at 90% or lower at 40%. Soil much darker. Water depends again on the angle of the solar radiation coming in. As I said, the sun glint will be high if the angle of incidence is very high, and so on. So, these are kind of the range of reflectivities. The one thing to remember is that the net reflectivity of the globe at the current time is about 30%, as we saw in the previous figure. So, again the question is, with global warming or with the past climate changes, how would this net reflectivity of the planet have changed? How would that have affected the energy balance? How that would have affected the circulation and hence rainfall distribution and so on and so forth. So, you probably are already aware that as the earth goes around in the orbital plane around the sun, it is an elliptic orbit. It is tilted to the plane at 23.5 degrees, as I said, in at the current time, and we know that there is aphelion and perihelion, the closest distance to the sun, the farthest distance to the sun, and so on. And the earth is pointing in the same direction. So, as it goes around, one hemisphere points towards the sun. Here the northern hemisphere is pointing towards the sun during summer solstice, boreal summer solstice, or the northern hemisphere summer solstice, and you go through an equinox where sun is on the equator. So, all latitudes on the equator experience the same length of day and night. The length of day will be different at each latitude, but at any given latitude the length of day and night will be the same during the two equinoxes. And when it is pointing away from the sun, we have our winter during the December solstice, and because of this tilt that we get seasons on earth, because if it was not tilted and going around straight like this, all latitudes would be seeing the same amount of sunlight all year long. So, you would not get any seasons. So, if you again look at the longitudinally averaged distribution of solar radiation with seasons. So, now we are showing a meridional section going from the equator to the poles, but we are also showing it by the seasons. Okay? So, this is showing that if you look at the southern hemisphere, during our northern hemisphere summer, they will have a winter, and during our hemisphere winter, they will have a summer. So, there is high radiation during its summer, but it gets no radiation during its winter. The same way for the northern hemisphere. And the tropics, if you look at draw a line across the equator or any of the low latitudes, the radiation changes, but not much. So, obviously, the seasonal contrast is very high as you go to higher latitudes, but as you stay at the lower latitudes, the seasonal contrast tends to be very low. This is not something very new to you, but it is good to remember this distribution of energy that is coming in. Why do we care? Because over long time we will see that over tens of thousands of years, this obliquity or the tilt itself changes from about 22.5 degrees to 24.5 degrees. The ellipticity of the orbit itself will change by about 2%. It will become less elliptic or more elliptic, and the earth, it precesses like a top, and also because of the gravity of other planets in the solar system, this orbit itself will wobble, and I will show an animation of it in another lecture. Those are essentially the orbital parameters, they will change either the amount of sunlight coming in or the distribution of sunlight, the seasonal distribution of sunlight, which will also drive climate change. So, these are the kind of relations between equator to pole temperature gradient, energy balance and the circulation, because it is all about moving energy from surplus regions to deficit regions. The other thing that plays a very important role in the climate, the circulation and the energy balance is water. Why? Because this is a simplified so called hydrologic cycle figure, which is showing that there are precipitations and evaporations happening all over the place. Precipitation can be rain. A lot of the evaporation that happens over the oceans, for example, falls back over the oceans as rain, but a lot of it gets carried on to land as clouds or as water vapor, and it will rain on land or it will be snow on land, and that water then gets into the rivers and lakes and groundwater, which will eventually flow back to the ocean. Why is water so important? Two reasons. One, water vapor is a very strong greenhouse gas. If you put water vapor into the atmosphere, it will also absorb the outgoing long wave radiation. The other reason is because water is taking the energy from where it is evaporating. If you remember your basic chemistry and water structure and so on, you have the molecule of H2O, and each molecule is slightly polar. So, they are linked to each other through the so called hydrogen bonds. So, when evaporation happens, those energy bonds are broken and that energy is taken with the water vapor, which means when the water vapor condenses in the atmosphere, that energy is released. So, you are taking energy from somewhere, lifting it up, either releasing it locally or moving it far away and releasing it over there. So, things like cyclones, hurricanes or monsoons, etc., are essentially energies being moved around. So, water is a very important player in the climate itself because of its moving energy, and also in climate change because it is a greenhouse gas. But we will see that there are many details that we have to worry about in terms of its distribution and so on. The other important thing that you have to remember about water, I think you already know, that when it is colder, the air tends to be drier, and when it is hot, it is more humid. Why? Because if you look at the relation between temperature going from minus 30 degrees centigrade to plus 30 degrees centigrade and the density of water vapor at saturation, it increases continuously. So, poles which are typically very cold at minus 10, 20, 30 degrees centigrade have very low water vapor content. As you come into the tropics, as temperatures increase, the amount of water in the air, in the atmosphere increases exponentially. This is important because any exponential relation produces nonlinear effects. For 1 degree change, you make much larger increase or decrease in humidity. This plays a very critical role because with global warming, we are warming the temperatures, obviously that is why we call it global warming, which means we are increasing water vapor in the system, which can drive more energy into the system, and then there are related effects like whether that will affect hurricanes, how it will affect hurricanes, how it will affect the monsoon, how it will make rainfall distribution more extreme and so on and so forth. So, water is a very critical player. The other thing we have not mentioned explicitly, but I am sure you have learned somewhere along the way, is because the earth is rotating, everything on earth has a tendency to rotate. It is like being on a merry-go-round. If you stand without holding anything, you are going to be pushed to the side, right. So, that is the Coriolis effect, and shown simply here, because earth is a sphere and each point is making one circle in 24 hours. The equatorial point has to move a lot of distance in 24 hours. So, it will move much faster, almost 1000 miles per hour, compared to some point away from the equator, which will move slower and slower because it is covering less and less distance as it gets away from the equator. So, this circular motion has something called a Coriolis effect, which means things that are moving at planetary scale, at large scale, will tend to be pushed to one side by this rotational effect, which is called the Coriolis effect. There are details about why we call it an effect and not force, but do not worry about it because we also use it interchangeably. So, the main thing to remember here is that if you are in the northern hemisphere, you are deflected to the right of the direction of motion. That is important to remember, to the right of the direction of motion, which means if you are going northward, you will be pushed to the east. If you are going from north to south, you will be pushed to the west. It is exactly the opposite in the southern hemisphere. You will be pushed to the left of the direction of motion. So, if you are going south here, you will be pushed to the east. If you are going north, you will be pushed to the west. That is because we are in space and the frame of reference is immaterial, whether you are looking this way or that way. So, we are, the effect we experience depends on which hemisphere we are in, just relatively speaking. So, if we put this together, we said there is energy surplus in the low latitudes, energy deficit in the high latitudes, we have to move it, and when things move, there is Coriolis effect. Taken together, we end up with this complex looking circulation. The good news is there is a separate module that explains this thing in much more detail, but I will give a short run out of this in this lecture. Basically, remember, more energy, more heating in the low latitudes. What happens when you heat the surface? The air is going to get warm and it is going to rise. Over the ocean, the air rises, takes the evaporated water vapor with it. Okay? And we will see the atmospheric structure or the temperature profile in the atmosphere in a minute. So, essentially, when air rises, then that air has to be replaced by other air, just for mass continuity, mass balance reasons, right. You cannot have a vacuum. So, if you move air up, some other air will come in. So, that air will come from both sides into the region where air is rising. So, you can see that air is rising here, it hits a ceiling here, which I will show in a minute. It will go poleward, and for various reasons it sinks and makes a cell here, and some of it goes forward and makes another cell over there. So, there are names for all of these cells. This one is called a Hadley cell. There is another cell here called the Ferrel cell, and then there is a third cell there called the polar cell. The other thing to notice is that as the air is trying to come into this region of where the air is rising, it is being deflected by the Coriolis. So, if it is coming from north to south in the northern hemisphere, being tilted to the right, from the southern hemisphere is being tilted to the left. So, you end up with these so called north easterly and south easterly winds. They are called the trade winds for historic reasons. They were used by traders for sailing and so on, and you get the opposite direction winds, so called westerlies at the mid latitudes, and you get the so called polar easterlies at close to the polar latitudes. Okay? And wherever there is heating and rising motion, there is also low pressure. Wherever the air sinks, there is high pressure. Okay? So, there is rising low pressure, sinking high pressure, rising low pressure and sinking high pressure at the poles. So, you have to basically stare at this for a while, listen to the other module that explains it in much more detail, and get used to the wind systems of the trade winds, mid latitude westerlies and polar easterlies. Wherever there is rising motion, as we said, water vapor is going with it. As air rises, it is going to expand and condense the air, water that is in it, which means it is going to rain. So, wherever there is low pressure, you are also going to have rain. So, this is showing evaporation and precipitation, and essentially where it is green, this line is where precipitation and evaporation are equal. Where it is green, you have more precipitation than evaporation. Where it is yellowish color, you have less precipitation than evaporation. So, essentially high pressure, high sea level pressure means more evaporation than precipitation. So, those are the deserts. That is where the deserts are over the ocean and over the land, as we will see later. Where there is convergence and low pressure, you have rainfall, more rain than evaporation. So, you have these bands of rain, dry weather and wet weather. Okay. Why does it matter? Basically again, the equator to pole temperature gradient determines how much energy you have to keep moving. For any reason climate changes means temperature changes, which means the equator to pole temperature gradient will change, which means the winds will change, the pressure distributions will change, they might shrink, they might expand. So, deserts might shrink, deserts might expand, and the rainfall distribution, the amount, the intensity, the duration of rain, etc., will change. So, we will look at specific examples along the way about how monsoon has changed with global warming, for example, or how it has changed in the past because of natural causes, etc. In that sense, this figure is very essential because it captures all the dynamics other than the detailed feedbacks that we talked about in terms of vegetation and atmosphere, ice and atmosphere, land and atmosphere and so on. But they are all embedded within it. So, we will look at examples as we go along. So, that is a very important figure to look at. So, just to add little bit details to the story, we have here the altitude in the atmosphere. The ocean is below the 0 line here, just as a detail. A line here called troposphere, which comes from looking at the temperature distribution. Okay. So, again if you look at a typical mean temperature at any location on earth, it looks something like this. The exact numbers change depending on whether you are in the tropics or mid latitudes or high latitudes, but the structure will look very similar. What is it? It has a troposphere where the temperatures are warmer near the surface, they decrease to a certain height of about 10 to 12 kilometers. Again, it depends on whether you are in the tropics or high latitudes. Then there is a change in the temperature gradient, and the stratosphere is actually getting warmer as you go up in height, and then there is a mesosphere which cools again, and then the thermosphere which goes up. So, this is where we live, and this is what we care most about, troposphere. It is called the temperature inversion, which means the temperature is warmer near the surface and colder up above. Okay. Because of the radiation hitting the surface and then the energy balance happening mostly at the surface, since the atmosphere is almost allowing most of the energy to go by. Of course, it keeps a lot of energy through water vapor condensing, etc. The surface gets to be warmer. This is the most important effect of a greenhouse system. If you do not have a greenhouse, then the surface will not necessarily be warmer than the atmosphere. So, the greenhouse provides this long wave and the energy balance to warm the surface. This place where the gradient change happens is called the tropopause. I briefly mentioned earlier that the stratosphere gets warmer because the ultraviolet radiation is bombarding the oxygen molecules here and generating ozone out of oxygen molecules. So, ozone is an endothermic reaction which absorbs the UV energy, and hence it warms the stratosphere. So, with global warming again or with climate change, we will be worrying about how this gradient changes, how will the tropopause height change, and that will affect all the processes of energy transport again, how strong the winds are, how much it rains, where it rains, how it rains, and so on and so forth. Again, there is a separate module with the full details of the vertical structure that you can study more carefully. As you can see, we are now connecting each of the concept back to global warming or climate change, because every one of them will keep playing a role in global warming and climate change. So, let us look at an example of all of these things together. We mentioned the distribution of radiation, differences in heat capacity, and so on. So, here we are showing the contrast of land and ocean. What do we remember? Ocean has high heat capacity, so it warms up slowly and cools down slowly. Land has low heat capacity, so it warms up rapidly and cools down rapidly. So, this will give you something called sea breeze on a daily time scale, right. When the sun comes up in the coastal regions, the land will warm up faster, which means the sea level pressure will be lower. The ocean will not warm up as fast, so its pressure will be higher. So, you will get winds going from high pressure to low pressure. So, you get sea breeze. At night the land cools faster, so it will be high pressure, ocean cools slower, so it will be lower pressure, relatively warmer. So, the winds will reverse. This reversing circulation we call sea breeze. The same thing happens on a seasonal time scale. Why? Because the sun is in the southern hemisphere during our winter months, the northern hemisphere winter months, and as the sun moves to the north, the land heats up fast, the ocean is heating up slowly, which means the pressure on land is going to be lower than on the ocean, and you have this large scale circulation of wind going from high pressure on the ocean to low pressure on land. When you look at the winds later on, we will see that again you have to add Coriolis to it. The wind cannot just go straight. Every time it tries to move, Coriolis will push it to the left or the right depending on which hemisphere it is in. Altogether, you are basically moving water vapor and winds from the ocean to land during the summer season, because land is heating up faster. That air is going to hit a mountain, for example, and rise like the Himalayas or the Western Ghats, and rising air always expands because the pressure decreases as you go up in the atmosphere, and that condenses the water vapor that is in it and it gives us rain. So, in the winter season exactly the opposite thing happens, where the sun is moving back towards the southern hemisphere. So, now land is cooling faster than the ocean, pressure gradients reverse, the winds reverse, and so on and so forth. So, India in fact has both a summer monsoon or a southwest monsoon, and a winter monsoon or a northeast monsoon, which we will see later on. Not everybody gets rain during the northeast monsoon, but those of you who know, the southeastern coast of India like Chennai gets lot more rain during October, November, December than in June, July, August, right. So, that is the large scale monsoon circulation. Again, the question is, with global warming, how will monsoons change? How much is the ocean warming because of global warming? How much is the land warming? And then there is additional complications. What happens to the dust in the air? How does the dust change with global warming? How does the dust affect the heating of the land and the ocean? How will that affect the monsoon? And one of the lectures will focus just on the monsoon processes and show that actually dust makes a huge difference on how the monsoon responds to global warming. So, you can see the feedbacks. Global warming is happening because of increases in greenhouse gases that affects rainfall and vegetation, but vegetation affects dust. Dust in turn affects radiation, which in turn affects the monsoon because of land heating differences, and so on and so forth. We have to always keep these feedbacks in mind, keep tracking them. So, the other simpler version of how rainfall is squeezed out of the system is the so called orographic precipitation. Anytime the winds are forced to go over a mountain, they go from high pressure near the surface to low pressure at higher altitudes, which means air will expand, water will condense, and you will get rainfall. So, if you look at typical mountains, on this side there is a lot more rain. So, you will have nice green forests. On this side it will be a rain shadow. So, this is called the windward side, it is called the leeward side, and you will get very different vegetation here and often no vegetation. This is like looking at rainfall over Mumbai versus Pune. Pune is on this side of the Western Ghats. So, the rainfall over Pune is much lower than the rainfall over Bombay, Mumbai for example. Okay? These are the important processes. The ocean is a bit more complicated. So, if you look at the winds we are showing here, the winds in the atmosphere can go over the mountains to the other side, and they can make a whole circle around the globe. Can the ocean currents do that? Not really, because there are land boundaries which prevent it from going over the land to the other side. So, when the winds try to drag the ocean currents, they hit the boundary. Along the way they are also deflected by the Coriolis effect, right, to the right in the northern hemisphere, to the left in the southern hemisphere, and so on. So, they end up creating these so called gyres, which are again high pressure systems in the ocean as opposed to the atmosphere, and typically the warm tropical waters are taken to the high latitudes on the western side of the ocean or the eastern boundaries of the continents, and cold waters are brought down on the other side. These arrows are different on this side because of some other circulation that I will mention either in this lecture or later on. The Indian Ocean circulation, you can see, is already very different than the Pacific or the Atlantic Ocean. Why? Because of the monsoon circulation. We said the monsoon circulation is this way in the summer and that way in the winter. So, the currents are also changing direction all the time. Why is this all important? Because remember, we said we are always trying to move energy from low latitudes to high latitudes. So, how the oceans move the heat from low latitudes to high latitudes depends on how the currents are moving, and how the currents are moving depends on how the continents are distributed, and there are additional factors which depend on the density of the water that we are talking about. What does the density do? Essentially, just like the atmosphere is colder at higher latitudes, ocean temperatures are also colder at higher latitudes. There is one other very critical factor in the ocean. There is salt in the ocean. The density of seawater depends not just on the temperature, but also on salt. So, you can make warm water more salty and make it heavier than cold water which is fresh. So, it is not just temperature. The temperature and salinity relation to density is very non-linear. It is like a fifth order polynomial which can create some very interesting behaviors which we might come back to later on. So, if again I look at a longitudinally average section in the Atlantic Ocean in the middle here, then you will see that at high latitudes in the Atlantic, this is around 65 north or so, there is so much evaporation happening. I am adding some complications now. When evaporation happens in the ocean, water vapor is taken away, but the salt is left behind. So, more the evaporation, more the salt left behind, which means the density gets higher and higher because evaporation cools the water and it adds salt to the water. So, there is something called North Atlantic deep water formation happening in the North Atlantic, which then the water sinks like a rock, flows south towards the Antarctic peninsula and comes up, and the edge of the Antarctic has so much ice formation and it is very cold. When ice forms, what happens to the salt? The salt is left behind. It is called brine rejection. So, more ice you form, more salt you are going to leave behind. This is for sea ice, not for land. Land ice or glaciers are formed by a different process. Okay? So, that forms something called Antarctic bottom water, because that is the heaviest water on earth. It is a bottom water that sinks even deeper than the North Atlantic. Okay? So, we have introduced several concepts here, but do not worry, we will come back to it again and again. But I wanted to show this figure here for two reasons. One, that circulation is not directly related to winds pulling the currents. This is related to temperature and salinity, right. So, that is thermal and haline, HALINE, haline means salt related things. So, this is called thermohaline circulation. It is a density driven circulation. Deep ocean is set in motion by these density contrasts. The wind forcing in fact does not reach that deep into the ocean. It only remains in the top 1 kilometer or so, and the ocean is almost on average 4 kilometers deep. Okay? So, that water eventually comes back up in the regions where winds are pulling up the water. How does that happen? You need some energy. Why? Because I will show in a minute that cold heavy water sitting at the bottom, warm lighter water sitting at the top is a very stable system. Why would heavier water move to the surface? Unless you give it some energy, think of it as a potential energy, right. This is, if you raise it here and let it go, it will just drop, that is potential energy. So, something is needed to convert that heavy water back to the surface, which we will see in a minute. But the other main thing I want to point out here is that when this water sinks from the surface, It takes everything with it. It takes the heat, it takes carbon dioxide, it takes any other chemical or organic matter and so on like oxygen. And these ocean is so deep that this water, as you remember, we said that the time scales are 100 to 1500 year time scales. Once the water sinks, to come back up, it might take it up to 1500 years, and some water is even older than that. So, this is the reason why ocean takes up most of the carbon dioxide, and it takes 90% of the heat generated because of human activities, which means the global warming is heavily controlled by what the ocean does, not just because it takes carbon dioxide, but also because it takes up heat. So, if on some day ocean decides I am tired, I do not want to take up any more carbon dioxide or heat, global warming can accelerate. Can it happen? We will see. So, this is the schematic of the so called thermohaline circulation. The Labrador Sea is very cold, ice forms heavy deep water. The so called Jin Sea or the Greenland, Iceland, Norwegian Sea is where lot of evaporation happens and heavy water forms. So, these blue lines are heavy cold waters that are sinking, they are flowing at the bottom to the southern ocean, which is all along here. Some heavy water also forms at the Antarctic coastlines, as we said, Antarctic bottom water. All those waters are mixed up, they go into the Indian Ocean, they go into the Pacific Ocean, and over long time they convert it back into the surface, heated up by the atmosphere and flow back towards where the water sinks. So, it is a long term circulation from sinking, mixing, going back to the north, getting converted to surface water and coming back. This is called the global thermohaline circulation in the ocean. So, again in terms of past changes, we will see when the plates moved and the continents were configured differently, where the water sank and where it came up would have been different. With global warming, then we want to be sure that this formation of deep water is not perturbed or not reduced, because that will reduce the amount of heat taken up by the ocean, amount of CO2, carbon dioxide being taken up by the ocean. And keep this in mind, Greenland is sitting right here. What does Greenland have? Lots of glaciers. What will happen to Greenland glacier with global warming? What is already happening? If the glacier begins to melt and it puts fresh water on this region, then what will happen to deep water formation? Remember, evaporation produces cooling and salt, but if it is very fresh water, there is less salt, which means less sinking. So, if you perturb this circulation, then global warming can get amplified. So, that is why these kind of circulations are very important in the context of change on long time scales and global warming. The typical profiles of temperature in the ocean, we looked at the atmosphere, it has a complex structure, troposphere, stratosphere, mesosphere, thermosphere. The ocean is somewhat simpler. If you look at the tropics, these are two lines showing summer temperatures and winter temperatures. Summer temperatures are warmer, but both have similar profiles. There is a well mixed layer here because of the winds, there is turbulence, they are constantly being mixed. So, the density is almost uniform. There is a rapid change in temperature and then it remains almost constant. Because this is a temperature gradient, it is called a thermocline. Again, there is a separate module explaining this. In the winter, even though you are in the tropics, there is some cooling, air is drier, so there is evaporation. So, you will get slight cooling. So, there is some seasonal change even in the low latitudes. As you go to the mid latitudes around 45 north, you will see that the seasonal contrast is much larger. When there is a summer and sun is heating the surface, there is strong winds and heating near the surface, but temperature is again close to 2 to 5 degrees at the bottom. But when winter comes, the surface cooling is very strong. When it cools, again it is heavy, so it goes down, so it mixes deeper than this layer. So, the deep ocean is hardly affected. You can see that the deep oceans, unless you go to the polar region, the deep ocean is not affected so much seasonally. At polar oceans, temperatures, you have to remember, this is warmer than here, this is much colder than either of these. So, even the warmest temperatures are quite cold and they are not as strongly stratified. So, the stratification or the temperature gradient or the thermocline is much weaker here, it is almost non-existent here. Okay? But still there is a strong temperature contrast from one season to the next. These have impacts on how much heat and carbon dioxide can be taken up by the ocean, how much mixing of colder waters can happen with the surface, and so on and so forth. But this also tells you why converting the deeper waters to surface water requires a lot of energy, because this water is always cold and heavy, this water is always lighter and less dense, lighter. So, converting this water requires a lot of energy, and it basically comes, I will say very quickly because we will not go into the details. There are lots of tides going back and forth. Those tides generate waves when they hit the mountains in the ocean. Those waves tend to mix up the water. So, over long time scales of 100 to 1500 years, this water slowly gets converted back to surface waters. A good exercise for you will be, how do we know that this water gets converted to surface waters? Okay? See if you can figure that out. So, this is basically a broad introduction to climate variability and climate change. Some of the take home points I want to re-emphasize are, Earth is a sphere. So, when sun's energy is coming in, more energy is intercepted per unit area in low latitudes, less energy at high latitudes. When you add ice and snow and the reflectivity, there is a net energy gain in low latitudes and there is a net energy loss at high latitudes. So, to keep the poles from getting colder and colder and the low latitudes from getting hotter and hotter, we are constantly moving energy from the surplus area to the deficit area, which is what gives us the weather, climate and so on. Short wave energy from the sun is heating everything and is getting reflected back to space as long wave energy. And Earth is special because it has this greenhouse layer that has given us a temperature that is very balmy compared to minus 50 degrees centigrade on Mars or 460 degrees centigrade on Venus. Is this why there is life on Earth? Well, now we might find life on Mars, but it is at least responsible for giving us water in all phases as liquid, vapor and solid phase. Is that really important for life? Maybe, but you can think through those things. Earth system components have different response times. So, we looked at the atmosphere, low heat capacity, land, relatively low heat capacity, ocean high heat capacity and so on. These things matter because the same heating produces very different response times in each component, which gives us multiple time scales of climate variability and climate change, even though the solar forcing is basically on a daily time scale and on a seasonal time scale. The feedbacks among the Earth system components generate many time scales and positive and negative feedbacks. I did not give any examples, but offline we will provide many examples of all the feedbacks. You can think already what they are. Deforestation affects evapotranspiration, microclimate and rainfall, right. Urbanization affects the long wave radiation, local evaporation and local microclimate. And heating a glacier reduces the glacier size, reduces its reflectivity and more energy is absorbed, which will make it warmer and melt more glacier. So, there are many thousands of such examples that we will go through over the course. Water plays a critical role in Earth's climate because it is able to stay in 3 phases, move energy around and it is a greenhouse gas. Okay. It is a universal dissolvent, it dissolves pretty much everything on Earth, that is also why it is so important. Ocean absorbs over 90% of the net energy. So, global warming is heavily modulated by the ocean. So, ocean, water together, they are very critical for what weather and climate we get, how it has changed over various time scales, and how Earth's climate will behave in the future with our activities. This is kind of a broad overview of weather, climate science, introduction to climate change, very brief introduction to energy balance. Now we will try to put these things in practice in various contexts of climate change over various time scales before we come back to the global warming as a whole in the end. See you next time.